I got friends in New York City, 'cause everyone I know left town.
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
Hello again. We'll start studying the rules of equilibrium by introducing the concept of center of gravity. Here we have an object with an arbitrary shape. And we would like to know, how do we define where does the gravity act in this object, if anywhere? And how can we find that location? In order to do that, we have to divide this object into small elements. So let's say we have, for example, just two elements in this case. And we evaluate the center of gravity respect to some point. The point can be chosen arbitrarily. So here we have the direction vector to the element 1 called R1, and here we have same for the other element, R2. And each of these elements have some mass. Let's call that would be M2, and that would be M1. The location vector of the center of gravity is the weighted average of product of mass and the position vector of the individual particles. So what does it mean mathematically? Here we have it. So the location vector of the center of the mass, or let's call it now center of gravity, is the sum of the individual products M1 R1 times M2 R2 and so on, divided by the total mass of the individual areas or masses, if you will. And hence we get this summation rule. Note that there are parentheses here, so you cannot just divide the sum m's out. Or in practice, we usually do this in components. So if we are in 2 dimensions, we evaluate the location of the center of the mass in x direction and y direction separately. In this example, the center of the mass would most likely be somewhere towards the heavier side of this object, so somewhere here, for example. So then we call this vector RCM, or let's call it CG, center of gravity. So we already mentioned these two concepts, so center of mass and center of gravity. They are the same thing if the gravity is uniform wherever this object is located. So for all the practical purposes, we can definitely make this claim. And why are we interested in the center of gravity? Turns out when in the equilibrium, when we need to calculate torques acting on objects, the situation is simplified because if we have the CG over here, center of gravity, then we can say that gravity is acting only at this point and all of the mass is concentrated there. And then the torque by this weight or the gravity on the object is simply, let's call it torque to the weight, about some point, this point O. It's just the cross product between the location of the center of gravity with the total weight of the object. And this simplifies the analysis of most objects quite significantly. let's see how this relates to equilibrium. So we have a simple rod, or it could be a pendulum, pivoted at the top. Center of mass is somewhere in between or in the middle. So mg that way, and the location of center of gravity, that's trying to make it straight. So that's going to be r cg, and here we have line going through the pivot point. So according to this expression, there will be torque because rcg and the gravity are not aligned. So if you use the right-hand rule, there is a clockwise torque acting on this object until it swings all the way down when rcg and mg are aligned. So as long as the rcg is aligned with the line of support, that means the center of gravity is directly or above the pivot point in this case, or the support point, there is no disturbing torque and the object will stay in equilibrium. But as soon as we are off axis or outside the line of support, there will be rotational motion. And here's a two-dimensional example. So we have a box on an incline that has enough friction so it doesn't slide down. So in this case, there is not only one line of support, but in fact infinite amount of those, because the box is touching the floor at infinite amount of points. So here we have the gravity mg, and here we have something called the area of support. So that's just a collection of those lines of support that I mentioned. And as long as the center of gravity is within that area of support, there is zero torque about any given point, and the object will stay in equilibrium. But what happens now if we tilt this incline a bit more? So in this case, the mg goes, in fact, outside the area of support. So suddenly the line of support cannot move with the center of gravity, and it is restricted to that corner point there. So then we have here the vector rcg, and suddenly we do have torque or net torque acting on this object, defined by the cross product rg times the weight, and there will be counterclockwise torque and the box will topple over if it doesn't already slide. And just to make this clear, so in this case the rcg is aligned with the weight, and hence there is zero torque. But as the CG starts moving to the left, there is only so far this pivot point can go, and here we have it tilting over and producing the disturbing torque. Let's do a simple example to illustrate these concepts. Here we have a sawhorse and has a length of 6 meters from end to end, and there's a person standing at the very end who has mass 40 kg, and then the mass of the plank itself is 90 kg. And we would like to know, does this thing tip over or not? To answer that question, we need to find where is the center of gravity of this plank person system. If it's within the area of support, which is between the two saw sawhorse supports, then we're fine. But if it's outside, then this will definitely tip. So how do we calculate the location of center of the mass for the system? So this is one dimension, so we can only analyze it in x direction. So what we have, the x coordinate of the center of gravity is from here. So the mass of the plank times its distance from some arbitrary point. Let's take the point to be here. So in this case, we have L over 2 for the plank, because its mass is concentrated in the middle. So, and then for the person, he's all the way to the other end. So also we have here mg acting in the middle, and little mg acting at the other end. So capital M at the middle at distance of L2 plus the person M at the distance of L from the arbitrary point, divided by the sum of the two of the total mass, M plus M, and we get 90 kg times L over 2, 3 meters, plus mass of the person times 6 meters, divided by the total mass, that's 130 kg, and we would get 3.92 meters. So it would be somewhere around here, so 3.3 meters in the middle and 92 centimeters is here. So it puts it past the furthest support, which is only 75 centimeters from the middle. So if our CG is there, then this system indeed does topple over. But let's calculate this location of, again, in a simpler way. Like I said, it doesn't matter where do you take the reference point. You can also take it here in the middle, and that simplifies things. So now the distance of the masses plank from this point is 0, and we only have contribution from the person who is now L over 2 away, then divided by M plus M. So in this case we get only 40 kg times 3 meters L over 2 divided by 130 kg. And this gives 0.92 meters. So we are 0.92 meters from the center, which is exactly the same result we got before. So you can be clever about choosing the pivot point and oftentimes make life easier.